using expressions and variables in there. So the expressions in A, we have 3 times 4 on one side and 4 plus 4 plus 4 plus 4 on the other side. Which one is greater? Which one's equal? 3 times 4 is 12. 4 plus 4 plus 4 plus 4 is 12, so it's equal, so you use the equal sign. Say 3 times 9 plus 5, that's 27, 32. 6 times 8 is 48, so you would use the less than sign. So in B, on the left side in the figure, we have blank plus 3, and we have 2 times blank. So let's put 5 in there. 5 plus 3 is 8, 2 times 5 is 10, so you'd use the less than sign. Or you could say, try 3. 3 plus 3 is 6, 2 times 3 is 6, oh, and this time it's equal. On the right side, in A, we have expressions, again, with variables. 4 minus 6x, and then we have 3 parentheses 1 plus x. So here we're going to move the plus 4 over, and we distributed the 3 to the 3x, the 3 to the 1, the 3 to the x. So now we have negative 6 minus 3 plus 3x minus 4. Negative 9x, because we moved we're going to subtract 3x from both sides. And then we have 3 minus 4, which is negative 1, divide by negative 9, and you end up with x equals 1/9. The number line is an important model in developing the concept of a variable. In the figure below, finding the variables are in a relation to numbers and in relation to other variables help to build the meaning of the variable. When students are looking at the number line, ask questions like, what is the value of the x? Could it be any number? If we don't know what x is, how can we place 1/3 x on the number line? Suppose you have a number line of 9, and then you have an arrow going over to a number that is question mark. That value from 9 to the question mark you could say is your variable, which could be s or could be any letter you could use in there. Here's 2 examples. Anna has $10. Noah has 3 more than Anna. How much money does Noah have? Or Anna has some money. Noah has 3 more than Anna. How much money does Noah have? Primary grade students can list possible ways in the table and eventually represent the answer as Anna plus 3 equals Noah. Or you could say A plus 3 equals Noah for number 2. And a table used to guide thinking and recording values. You are buying a $1.75 pencil and a $1.25 eraser from the school store and want to spend all of $35. What equation represents the situation? Once students have the equation, in this case it would be $1.75x, because we're not sure how many pencils we can buy, and $1.25y, because we don't know how many erasers to buy, equals $35. Ask the students to tie each number and variable back to the context, because we're going to try to spend all $35. So if we were to buy 20 pencils at $1.75, that would come up with $35. So 0 erasers at that point. But what if we bought 28 erasers at $1.25? That would be the 35, and then we wouldn't buy any pencils. And there's other combinations where we could have pencils and erasers in the same equation. In the figure below are a series of examples that show problems in which each different shape on the scale represents a different value. When no numbers are involved, as in the top 2 examples of the figure, students can find combinations of the numbers for the shapes that make the balances balance. If an arbitrary value is given to one of the shapes, then the value for the other shapes can be found accordingly. Problems of this type can be adjusted in different difficulty for students across their grades. The last three problems are on scales, and therefore the shapes have an unknown value that can be determined through reasoning. So if you looked at 8 and 12, 2 blocks plus a ball is 8, and 3 balls is 12. How much does each shape weigh? Well, I would say the 3 balls weigh the most, and the squares weigh the least amount. So I would say 3 balls is 4 each. So on the left side where it's 8, 1/2 of that 8 goes to the ball, so the square in the other square is 2 and 2. Mathematical modeling has a more precise meaning. It is a process that uses mathematics to represent, analyze, and make predictions or otherwise provide insight into the real world phenomenon. Let's compare possible ways to engage students. Number 1, 14 times 25 is equal to 7 times 50. True or false? You would have students on one side show 14 times 25 worked out correctly, and make sure they justify their answer, and then 7 times 50, and make sure they justify how they worked that answer out, and then they would compare and contrast the left side to the right side, and then put down true or false. And number 2, she wants to read 25 books over the summer vacation, which is 9 weeks long. How much does she need to read each week? This would be a type of division problem. How many? She has 9 weeks, but she has 25 books she wants to read. So 25 divided by 9, have the students justify their work and explain why or how many books each week she would need to read. Thinking the equal sign means, and the answer is, the revisit develop the concept of the balance, such as two pay imbalances, true-false questions, or open sentences. Thinking an equation is written improperly if it is not in the form of A plus B equals C. Use a variety of equation formats all year long. Make sure you have the answer on the right side sometimes on the left side. You have 6 plus 14 equals 22 divided by 2. Just make sure you have a variety of different styles of the equation. Thinking the variable is a label rather than a quantity. Make sure you define what a variable is. Emphasize it means the number of a quantity. Check a few examples to decide if something always works. Make distinctions between testing and proving. Encourage the use of visuals and manipulatives to show if it is true of any number. Confusing the variable x for a multiplication symbol. Use other variables such as n instead of using x. Simplifying expressions involving variables, ignoring the variable or the need for the parentheses. Use concrete representations such as a bag that some tiles to represent x, so 5x is then the 5 bags. Ask students to say the meaning of the expression. Matching words with equations and solving story problems. Begin by asking who is older, or ask students to substitute in numbers to see if the equation fits the situation. Interpret inequalities and their solutions. Use context and the number lines. For example, Allison has $5. How much might she spend at the store? Well, she could spend 5, 4, 3, 2, 1, or even nothing. Determine the equation for linear situations, particularly when the form of y equals mx plus b. Remember, m is your slope and b is where it crosses the y-axis. Use the diagram in the table to say what stays the same and what changes. Consider using the table with extra columns Ask students what stays the same and what changes with each step.